Hello and welcome again back to lecture 3 of our course on advanced plasticity of solid continua. So in this lecture we will be continuing to talk about the strain measures. Specifically we will talk about the objectivity of strains, the frame indifference aspects, and also we will be talking of the time rates of strain rates, which are very important in plasticity especially. So, and we will see if strain rates are also objective. Now, towards understanding what exactly objectivity is related to the frame indifference of the possible rotation of the coordinates or possible translation of the coordinates, or together both rotation and translation of the coordinates in the spatial configuration, that is in the deformed configuration. So if you consider small x to be the coordinates of the deformed configuration, then what it means is that we are talking of a rotated and translated coordinate system also, right. So this rotated and translated coordinate system will be described by x star, whereas small x is the original coordinate system that you have chosen for the spatial configuration. So x star and x are related by a rotation of the coordinate systems given by a space independent but only time dependent proper orthogonal tensor Qt, which is a rotation matrix, and basically a vector Ct, which is the translation, right. So both Q and C, you will observe, are functions of only time and not space. Specifically what this means is that Qt is a special orthogonal matrix or transformation. It means that its Q transpose Q is I, that it is orthogonal. Its determinant is +1 and not -1. And this SO3 means it's a special orthogonal group of all such rotations. For example, if you think of the identity of this group, it is just the identity rotation, that means no rotation at all, okay. So that also belongs to SO3, this group. If you compose two rotations, let us say Q1t is one rotation and Q2t is another rotation. If you compose them, Q1 composition Q2, that will also be a proper orthogonal rotation, okay. So proper rotation. So that will also belong to SO3. And Q inverse, which is basically Q transposed, that is also a rotation in the other direction, in the reverse direction, right. So that also belongs to SO3. Any group of elements has this property, right, that the identity has to be identified, that is the identity transformation in this case, right. Then the composition has to be identified, and it has to be ensured that the composed element is also an element of the group, and the inverse must exist within the group. So this group is called the special orthogonal group, okay. All rotations belong to this special orthogonal group. Anyway, so the question why we are doing this change of coordinates here from x to x star is that we want our constitutive equations, the equations that relate stress to strain or stress to strain rates, etc. in plasticity. This should not depend on the choice of our coordinates, right. The physical world, the expressions that we have for the physical world for modeling them, should not depend spuriously on the specific reference that we choose, right. So that is why we basically in this case require that if there is a superposed rigid body like transformation of the coordinate frames, which are characterized by Q and C, then this transformation will not affect our constitutive equations, okay. So this is essentially the idea behind and the principle of material frame indifference. Now I would recall your memory, jog your memory a bit to the facts that we already know, that the deformation gradient is given by the gradient of small x with respect to the capital X. Recall that capital X is the coordinate cover for the referential configuration, right. Now let us understand what happens to the deformation gradient itself under a change of coordinates in the spatial configuration. The referential configuration, for that the coordinates remain the same, right, but the change of coordinates applies only to the spatial configuration. Under this change of coordinates from small x to small x star, how will the deformation gradient look like? For example, if the deformation gradient was f under small x, then under small x star what would it be like, right? So if I call that modified deformation gradient to be equal to f star, then we can easily show that f star is given by q times f. Q is the rotation matrix, okay, on which basically entail the coordinate transformation in this spatial configuration. To understand why this is so, why f star equal to qf, we have to understand that, okay, we have to recall that x star is basically qx plus c, q and c being functions only of time, and then let us try to find the deformation gradient f star as del x star by del x here, okay. So that by chain rule will be simply del x star by del small x times del small x by del capital X, right. So the gradient with respect to small x of x star times, here times means matrix multiplication, the gradient of small x with respect to capital X. Now the first term is nothing but q, gradient of x star, small x star with respect to small x, right, and the other multiplying term is the original f, gradient of small x with respect to capital X. So we basically have qf in the process, which is nothing but f star. So basically you see that f star transforms like qf, right. Now so this is not an objective transformation in the sense that if we were to have an objective transformation, then f star would have basically been qfq transposed, but that q transposed post multiplier is missing here. So f star cannot be considered to be an objective kind of a tensor. That is obvious because of the fact that f deformation gradient has two legs, one on the reference configuration and the other on the deformed configuration, okay. So that is the reason. And that is the reason also why we really cannot use the deformation gradient as a direct measure of strain, even though it is very useful in finally characterizing strain. As you will see here, we have already seen that C, the Cauchy-Green strain, is basically f transpose f, all right. Now let us talk about what happens to C star upon the change of coordinates in the spatial configuration. So C star obviously is a purely material tensor, right, purely material matrix field. That means the C star can be constructed purely in terms of the coordinate capital X. It has nothing to do with small x. So therefore it is understood, even before we do any calculations, that C star should not be affected by the spatial change of coordinates. This can also be seen from here, that C star by definition is f star transpose f star. Now use the fact that f star is qf, so we have in the process this quantity, okay, here replacing f star and f star transpose, and we use the fact that q transpose q is identity, so we basically get C itself. So C star is equal to C. Similarly, we have E star. E is basically the green Lagrange strain, which is related to C star, which is related to C through half C minus I identity. This identity, recall, is an identity sitting on the reference configuration. It is an identity on vector transformations where vectors live in the reference configuration, okay. So this identity leaves those material vectors unchanged. So we clearly have E star is equal to E as well, because C star is C, right. So, so basically we can clearly see that this is not just material indifferent, this is material coordinate indifferent, but this is coordinate invariant. So, C and E, these are coordinate invariant. When they are coordinate invariant like this in the material coordinate systems, we also continue to call such tensors as objective. Okay. So, we do not only call spatial tensors which transform like proper tensors, as objective, but also the material tensors which are basically frame invariant. So, so as I have said here too, that E and C, both the strain measures, material strain measures, are frame invariant. They do not even depend on the choice of your coordinate system in this spatial configuration. Now, this is another form of strain. This is the spatial form of strain, which is obtained by F transpose. This is also called the Almancy strain. Okay, Almancy. I have not introduced it earlier because we won't be using it much, because we don't really do our numerical work in mechanics. Being a solid mechanician, we don't do that in the spatial configuration typically. Okay. But anyway, this is useful to understand the basic idea behind objectivity. So, you can understand that B is a purely spatial tensor because F transpose takes a spatial vector, converts it into a material vector. That material vector is input to F, which produces, after taking that material vector as the input, a spatial vector. So, basically what we are getting here, we are inputting for B a spatial vector and getting back a spatial vector. So, it's basically another measure of strain, but it is basically a spatial strain measure, right. Now, let us understand what is B star. So, this is called the Almancy strain, right. So, you can easily put F star equal to QF here to show that B star is QB Q transpose. Now, those of you who are quite familiar with linear algebra, which you should be before taking this course, they know that this is one of these similarity transformations that we come across in linear algebra, right. So, that is what I have said here, the spatial tensors transform by similarity. If that sort of a similarity transformation where this matrix governing this similarity transformation is this Q rotation matrix for the coordinate change, then we say that this B is frame indifferent, right. This is not frame invariant because B star is different from B, you see, but it is frame indifferent and hence objective. So, this is so we understand therefore that the objectivity requires a proper transformation to be introduced in the description of all spatial fields. Right. Now, let us understand how basically the length change occurs in defining the strains, right, because strains are related to change of length, right. So, we basically know this already, we have seen it from the definition itself of the deformation gradient. We have d small x, which is an infinitesimal line element in the spatial configuration, is related to the infinitesimal line element in the material configuration or referential configuration through f, dx equal to f d capital X. Now, you take the dot product of d small x with itself, and on the right hand side you take the dot product of f d capital X with itself, and then do a little bit of small algebraic manipulation, very small, because f d capital X dot f d capital X will simply be d capital X dot f transpose f d capital X, right. That is by the definition of transposition of a matrix. So, f transpose f being C, we can easily see that this is basically the representation of the lengths, squared length, squared infinitesimal length in the referential configuration here. The referential spatial length change, squared length change is related to the material the same quantity in the material configuration through this metric C, right. So we can write this also in terms of the not just the metric C, not just the Cauchy-Green strain, but also by the Green-Lagrange strain, and therefore we can call this by 2 dx or half. Just put the relationship between C and E, and in the process we can show that dx, this squared change in length, change in the squared length rather, okay, in the spatial and material configurations is simply given by this quantity, all right. So this follows directly from the previous step. Now therefore you can clearly understand that essentially what the strains mean is in the material configuration is basically a measure, it measures the change in the squared length, okay, in the spatial versus the material. Right, but the linearized small strain, which is pretty well used in the literature because of the, or by the practitioners also, because it's much simpler to use with much simpler computational tools for that result in the process. The small strain is basically the, maybe we have discussed it earlier, it is basically half of grad u plus grad u transpose. Recall that u is the displacement vector, and not vector in the usual sense of vector being in the tangent space, but a vector in the sense that it has 3 elements in the 3 directions, 3 coordinate directions. So there where displacement u is defined through I minus grad u being this deformation gradient, right. Now this is the small strain, right. In deriving this small strain, you can derive it from capital E by actually neglecting all the nonlinear terms in U that arise in capital E because of the term F transpose F, okay. So there will be a quadratic term of gradient of U with itself that you have to remove and then get this, okay. So let us understand what happens to epsilon, the small strain under rigid rotation. So think of the deformation for rigid rotation, right. So in that case the displacement will be just q minus I times capital X, right, from the definition here itself, okay, definition of the deformation gradient. Now if you put the gradient of u here with respect to capital X, you get q minus I, correct, and that gradient if you use here, this gradient here are gradients with respect to capital X. So because u is defined only in terms of the material structure, in terms of the undeformed configuration, referential configuration, then you can see that if I do a change of coordinates, pure change of coordinates using rotation as well as translation, then what happens that we get epsilon to be equal to something like q plus q transpose minus 2I, something like that, which is not 0. So you see what actually we have come to conclude is that under change of coordinates which is purely rigid and therefore should not introduce any new strains, this epsilon, which is the small strain, changes, so which is unphysical. So therefore this linearized strain is not objective. So if you are looking for analyzing a body, a solid body under large deformation, then this linearized strain won't work. Small deformation it is fine because the errors don't accumulate much, but for large deformation it is inadmissible. Now let us understand also what are velocity gradients and decomposition. So velocity gradient probably we have discussed earlier or not, it does not matter, but it is basically, first let us come to the issue of velocity itself. So velocity is the material time derivative of the deformation, okay. So deformation itself is small x, it is also called phi, it is in the range of, small x is in the range of phi t of capital X, right. This is equal to small x, you recall. So therefore velocity is the material time derivative of phi with respect to material time with respect to t, and whilst holding capital X fixed, right. Now the velocity gradient is nothing but the small grad, that means the gradient with respect to small x of v, which is nothing but L, the velocity gradient, right. Recall that here the gradient is with respect to small x, not capital X, right. So because v is now looked upon as a spatial vector, not a material vector. V has a representation in the material as well as spatial configurations, but we look at v right now as a spatial vector, right. So this is my velocity gradient. It's also a matrix because v is a vector. If you take a gradient with respect to another vector x, then it becomes a matrix. Now the thing is that like any matrix, any 3 by 3 matrix, it also has a unique decomposition in terms of its symmetric part, which is called the rate of deformation d, and an anti-symmetric or skew symmetric part, which is called the spin, right. So W is called the spin, it is skew symmetric, d is the rate of deformation, it is symmetric. Okay, so by definition therefore d, the rate of deformation, is half of L plus L transpose, and W is half of L minus L transpose, the way we decompose a matrix into its symmetric and skew symmetric parts. Now we are interested in understanding how L, the velocity gradient, will also transform under change of spatial coordinates, right. So now if I take, this is not a material line element, I am sorry, so this is basically a spatial line element, okay, a small line element in the spatial configuration. Now let us take the squared distance dx dot dx and take its time derivative. Then one can easily show that this is nothing but 2 dx dot d, capital D dx. This one can see from here. See, this dx dot is nothing but dv, right. That is related to the velocity gradient through L dx by definition of the velocity gradient. And now you take a dot product of dx dot with itself here, then and just add, so take a dot. So basically what you do, you actually do this time derivative here itself, okay. So basically this is the ddt of dx dot dx, you get dx dot dx plus dx dot dx dot, which actually comes to be equal to 2 times dx dot d times dx, right. This symmetric part comes and plays a role here. If you talk of the non-symmetric part of L, what happens is that the dx d small x dot w, the anti-symmetric part, times dx is 0, right, by the definition of the fact that w transpose is minus w. So basically what is happening here is that any change of length for the vector dx, for the small line element, or any change of angle, you understand that dx dot dx is not just a measure of the change of length but also a measure of change of angle, right, because the dot products talk of both. So those are captured purely through d, the rate of deformation, the symmetric part of the velocity gradient, and not through the anti-symmetric or the skew symmetric part w, right. So no change of length and angle of vectors due to w. So w is a local generation of rigid body rotation, okay. If the motion is known to be rotational, completely rotational, then w can be set to 0 if you know it a priori, okay. So now let us quickly talk of the skew symmetric matrix a little more, because we will be using it in our work quite often. Specifically, let us talk of what is an axial vector of a skew symmetric matrix. Some of you may already be knowing it. So let us talk of a 3 by 3 skew symmetric matrix W. Any 3 by 3 skew symmetric matrix over the real field can be represented by this, right, where W1, W2 and W3 are 3 real numbers, okay. Now, if I construct the vector W as W1, W2 and W3 column vector, all right, because there is a transpose here, then this is called the axial vector of this skew-symmetric matrix capital W, right. And we write capital W is this square bracket small w cross, okay, that is the notation we typically use. So, you can think of the axial vector as the axis about which a very infinitesimal deformation is taking place, because this capital W represents that, an infinitesimal deformation about the axial vector. Okay. Now, so basically given any vector, I can think of it to be the axial vector of some skew-symmetric matrix, right. So, you think of two vectors now, A and B, take the cross product, that will also be a vector, right. Now, the skew-symmetric matrix corresponding to that vector can be shown to be just this, okay. This is called the commutator. So, there is a skew-symmetric matrix corresponding to A, call small a, call this as capital A, this is skew-symmetric. Similarly, this is capital B corresponding to the vector small b, and this is capital B and this is capital A. Given two matrices A and B, AB minus BA is called the matrix commutator, right. So, basically you get something like that. Okay, so these kind of notions will be useful later on. So, I just wanted to just touch upon it. Now, another slide before I go for a quick breather. So, now let us take two material points x and capital Y, okay, and define the corresponding deformation corresponding to both capital X and capital Y. So, they are phi t x and phi t y. The distance between them can be captured by this quantity delta t, which is the modulus of phi t x minus phi t y. If the motion is rigid, then the distance between 2 points do not change upon deformation, right. So, therefore, d dt of this delta t has to be equal to 0, right. Now, let us do one thing, let us take the delta square instead of delta and differentiate with respect to time. Then we immediately get that small x minus small y, right, times basically a dot product with v at x minus v at y equal to 0. So, you see that for rigid body motion, the distance vector between 2 points in the spatial configuration is more or less is actually perpendicular to the velocities, difference of velocities at these 2 points, right. Now, we can actually go further down with it to show more things regarding what happens to the deformation, the L, that is the velocity gradient, when the deformation is completely rigid. But we will just take a small breather for the time being. We will come back after the breather. Thank you very much.